Welcome to UGC Net and Gate Computer Science student. In today's topic, I will be discussing data structure and algorithm for June 2020 examination. I'll be discussing all the problematic question which was asked in June 2012 to December 2019 from unit 7, which is data structure and algorithm. You can reach me for any help or doubt at this adiugcnet at gmail.com. Okay, so now straight away I'm going. Before going to explain all the question, I want to briefly give you some idea about what are the kinds of types of problems they may ask in this data structure and algorithm. Okay, usually we'll be starting from binary tree, in the sense it will be in order, pre-order, post-order they'll be asking. If it is binary search tree, they'll be asking which representation is a binary search tree. Otherwise, what is the left node, right node, like that they will be asking. And one more very important question from this binary search tree is nothing but which of the tree is eligible for representing binary search in such a way that we can search particular data. Okay, so that is another question. Next, with respect to heap tree, okay, nowadays many semester in which it was asked, max heap min if kind of problem. And then you will be having, once we go for algorithm, so very famous kind of question is knapsack problem, and then greedy tape optimization problem. And then basically we have stack and queue. From that they will be having some its operation with some elements, so they will be going. And then another very important concept here is the recurrence relation. Okay, so we'll be solving recurrence equation and then find the time complexity with help of this master theorem. Then they'll be even asking minimum spanning tree using Kruskal algorithm, Prim's algorithm. Yeah, many time they were asked using this Kruskal algorithm. Okay, and these are the syllabus. Syllabus is very simple here, and if you understand all the concept, okay. Now I'll be discussing problem, and before that I want to outline what are the time complexity for which are the types of concept in data structure. If you are going for array, in order to add the data, we need time complexity is 1 because it is linear. Okay, to remove particular data we need to check with all the data element linearly, so it is a big O of n. Okay, like that linked list I am discussing here, inserting what is the time complexity, and inserting at head, it is time complexity big O of 1, but anywhere other than head we need to compare with n data. And deletion, like that at head we will be using same time complexity as insert at head. Then anywhere deletion big O of n, then search, surely it is big O of n, like that. Okay, so like that we are going for W is in linked list. And stack, if you are going, so here big O of 1 for push pop, and even top of the data we want to find out, for that also big O of 1. Searching for that it take big O of n. Okay, and like that for sorting here, usually if ordinary sorting like selection, insertion, bubble, it will be taking big O of n square for worst case. And then if you are going for a radix, it is a big O of n. Then for if you are going for special kind of algorithm, kind of sorting algorithm, surely it is what n log n. Usually in general sorting take big O of n square. You'll be using 2 for loop to work out the algorithm. But in case of whichever sorting in which, if you are using tree, then you take I mean less than n square, that is n into log n. Okay, and like that merge sort, quick sort, and like that for searching also, for n comparison sequential search take big O of n, but binary search take log n. Okay, and like that Fibonacci search also take log n, which is less than big O of n. Okay, and I mean we know already matrix addition, I mean n into n addition we are performing, so it is n square multiplication n power 3. But repeatedly many times they were asked, okay, special kind of multiplication is called Triassian matrix, so where this will be taking n power 2.81, which is less than n power 3. Okay, and like that what is the time comes for BFS DFS is a big of number of vertices plus number of edges. And if you are going for I mean binary search tree, then its time complexity is log n. For worst case is log I mean sorry, big O of n. Okay, I mean binary search tree, AVL tree, red black tree, all are and even split tree, all are special kind of trees. For that for insertion, deletion and search, for all repeatedly it is log n. Okay, so now next one is I mean Bellman-Ford distance vector routing algorithm. For that I mean n into m. Okay, and Floyd-Warshall algorithm, it take n power 3, and I mean minimum spanning tree. For that Kruskal algorithm take m into log n, and whereas Prim's algorithm take m plus n into log n. Okay, so usually very efficient algorithm is Kruskal algorithm. Okay, so like that if you are going for E for priority queue, so finding max min big O of 1, but deletion take log n, like that insertion also taking log n. And next hash mapping, hashable odds, hash set. Okay, all take insert deletion big O of 1 only. Okay, so in order to resize the hashing, it make big O of n. Okay, so now we are going for a question. I mean in December 2019 it was very I mean interesting question here. The weight of minimum spanning tree is in the graph G calculated using Kruskal algorithm. Okay, it's actually very simple thing. They were represented a graph with edge cast. Okay, and we want to visit from any node to all other node without loop, in such a way that you want to visit all the nodes within minimum cost. Okay, that is the minimum cost spanning tree. So first let us assume we have I mean node here, node here, node here, node here, node here. You represent node, 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 node. Okay, now what is Kruskal algorithm? So it's very simple. Initially it will expand its edges with least cost. Okay, here 2 is least cost, then 3, 4, 5, 6 up to 8 there. So 2 is least cost. I'm first initially I'm expanding from this node to this node. Okay, next one is I mean next least cost is 3, so that is here to here. Okay, then after that next one is 4. Okay, so for this, while we are I mean taking and expanding in this particular minimum cost spanning tree, if we are taking minimum edge and connecting in progress in such a that if it is closed loop, then you want to skip such a minimum cost. Okay, now no problem with this 2, no problem with this 3. Okay, so far this one connected, this one connected. Now 4 is there, we are connecting here. Okay, one more node we yet to visit here is only this node. Okay, that is here. Okay, now what happens is after 4 we are try to find minimum cost as 5, but what happened, if you are connecting this 5 here, you will be getting close to path. Okay, so you want to skip that. Next minimum is 6. Okay, that is the node you want to actually visit. Now I'm connecting here. Okay, so now what is the cost? 2 plus 6 plus 4 plus 3. Okay, 15. Okay, so our answer is B. Okay, so next one is I mean so last semester it was very interesting because actually they represent only single graph, and from which they were asked 5 questions. Okay, a flow graph f with the entry node 1 and exit node 11. Entry node is this one, exit node is this one. Okay, so now one of the question is how many predicate nodes are there, and what are their names. Okay, now we want to know what is a predicate node. Okay, a predicate node is a node that it contains following conditions. Okay, so it should have at least 2 outgoing edges. Okay, so now if you are coming for this one, this is a entry node, the exit node. Okay, if you are taking one, is there any 2 outgoing edges? Yes, from 1 to 2, 3 it is going, like that from 1 to 11 going. Okay, now one of the predicate node is what, 1. Okay, so 1 is present only in option A and B. Okay, so let us assume we can skip this one. Okay, so we can skip this one. So now we either it may be or it may be. So next we are looking this 2, 3 a single node. So for that 2 outgoing edges there. So it is now 1 and 2, 3 are predicate node, and then 6 we are looking. So 6 also 2 outgoing nodes. So it's a 6 also predicate node. Is there any other node other than 1, 2, 3 and 6 as a predicate node? We can check. If we are checking 7, only 1. If we are checking 8, only 1. If we are checking 9, only 1. If we are checking 4, 5, only 1. If we are checking 10, it's again only 1 outgoing edges. Okay, so now answer is 3 number of predicate node. Those are 1, 2, 3 and 6. Okay, so now option A is very correct. Okay, so now same graph for which the second question was a flow graph f with the entry node 1 and exit node 11 again. So now question is how many region are there in flow graph. Okay, so region is very simple, right? Okay, and we have closed path, that is said to be region. This region there, this region there, this region there. Okay, we can easily find out. Okay, so now what is the usually any flow graph should have following condition. Okay, condition number 1. Okay, so it should have some number of closed cycle and outer cycle. Usually any flow graph we want to count one outer cycle. Okay, that is default. For next we want to find out what are the region. Okay, and inner regions, closed cycle. So here we'll be having okay, so straight away we can easily find out. From 1 to 1, 2, 3, 4, 5, 10, it's one region. Okay, like that 2, 3 sorry, yes, again we'll be having 2, 3 and then 6, then followed by 7 or 8. Either for this particular this region 2, 3, 6, 8, 9, 10, 4, 5 we can do. Okay, already so this is another region 6, 7, 9, 8, and 1, 2, 3, 4, 5, 10 is another region already calculated. Okay, so now number of inner closed circle is 3, and by default we want to take one outer circle, outer cycle. So it will be 1 plus 3, 4. Okay, so okay, next one is a flow graph f with the entry node again same. And what is the question? What is the cyclomatic complexity of flow graph? Okay, and we have two very famous formula to find out cyclomatic complexity for any graph is nothing but V of G. This cyclomatic complexity of G is nothing but number of edges minus number of nodes plus 2, or V of G equal to P plus 1. Okay, which means P stand for predicate node. We already counted, I am calculated predicate node as value as 3 plus 1 4. Okay, so now cyclomatic complex is 4, otherwise we can easily find out with this formula. So we want to count actually how many number of wedges here is nothing but 11. 1 2 3 4 5 6 7 8 9 10 11. Okay, so 11. How many number of node is nothing but 9. 1 2 3 4 5 6 7 8 9. Okay, so now 11 minus 9 plus 2. Okay, so 4. Okay, so we have two formula, whichever you prefer you can do it. And next question is again same problem, for which how many nodes are there in longest independent path. Okay, so now we can have longest independent path they are asking. Okay, so which means we want to go from one extreme node to another extreme node. Okay, so for example 1 to 2 comma 3 I can visit, and then 6 and then 7 and then 9 and then 10 and then 1 and then 1 I am going. Okay, so this way I can go. Okay, like that from here we can travel here and I am going. Okay, so that way longest path is what, 1 2 3 4 5 6 7. Okay, so not only 7, we are so again it will be going here. Okay, just imagine we are moving here like this and going here, again we are going here. Okay, so totally again from 1 we are traveling to 11, so it is 8. Okay, so I think this was the last question. How many nodes are there in flow graph F? Okay, so it is very blind kind of question, right? Okay, so totally 9 nodes there, so that was answer. Okay. Okay, so next if you are going for December 2018 question, in a ternary tree the number of internal node of degree 1 comma 2 and 3 is 4 3 3 respectively. Number of leaf node in the ternary tree. Okay, and actually it is very simplest formula kind of question for ternary tree. Ternary tree in the sense what, for every node 3 child will be there. Okay, so that is a ternary tree. The number of leaf node is nothing but sum of product of all internal nodes with its corresponding degree minus number of internal node plus 1. They say that number of degree for number of internal nodes of degree 1, for what is the meaning here is 4 node having 4 internal node having single degree as 1, like that 3 internal node having 2 degree as degree, then 3 more internal node having its degree as 3 each. Okay, so now 4 into 1 plus 3 into 2 plus 3 into 3 minus number of internal nodes, they said that what, 4 plus 3 plus 3 10 plus 1, so it is what, 19 minus 10 plus 1 10. Okay, so that is the formula. Okay. And next one is again Kruskal algorithm. What is the minimum spanning tree for this this one? Okay, so here what I can do is, if not mentioned where we want to start, we can take any minimum node. Okay, sorry, minimum edge cast as initial start. Okay, so just very simply what we want to do here is we'll be having these are the node. Okay, how many node there? 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8 9. Okay, totally 9 node there. Okay, just without this connection, you just imagine you represent outerly 8 node and innerly single node. Okay, now we take this one with the Kruskal algorithm. Okay, I can take initially this one or this one or this one, no problem. Okay, suppose I am taking this one. Okay, so I am connecting for now. After that next minimum edge is what, again this one I am connecting here. After that next minimum node is what, this one. Okay, I'm connecting here. Okay, after that what you want to do, I want to any more one, no. Okay, I can take 2. Okay, so now here we have 2, here we have 2, here we have 2. Okay, anything you can take. Suppose I'm taking this one. Okay, so now what happen after connecting this one, I can take either this 2 or this 2. Okay, suppose I am taking these 2. Our aim is you want to visit all the node with the minimum cost. Okay, so no problem. Again, if you are taking this 2, now this will be closed path, you want to skip that. Okay, and so now so far we done and in this 2 also I can connect because no closed path. Okay, after that I mean any more 2, no. Okay, next one is I want to go for 3. Okay, so here this 3 there, this 3 there, and then yeah, only 2 3 there, right? Okay, suppose I mean if I take this 3 here, this will be closed path. Okay, so I want to skip that, so but I can take this 3, so after that 4. Okay, so if I take this 4, it will be closed path, I don't need. Okay, and only node we have to visit is this one. For that I can use this 4. Okay, so I'm connecting. So now totally what is the minimum cost? 2 plus 3 5 8 8 11 12 12 plus 4 16. Okay, 16 is answer. Okay, so next one is here binary search tree constructed by inserting following number in order. I mean these are the nodes, the number of nodes in left subtree. Okay, so for that I want to construct what is called binary search tree construction. Initially we take first data, we can keep it as what is called root node. Then suppose 25 coming, I want to compare this 25 with this 60. If it is lesser, we want to keep in left side. If it is right, we want to keep it in right side. Okay, so 25 is less than 60, so I'm coming and I'm representing here. Okay, then 72 is coming. So now what happened, we want to compare with root node. Okay, 72 is greater than 60, I'm going and placing here. Now next one is what, 15, so comparing less than, coming here, again less than, so I'm placing here. And like that 30, less than 60, coming here, greater than 25, I'm placing here. Okay, now 68. Okay, greater than 60, coming here, less than 72, I'm placing here. And then 101, greater than 60, coming here, greater than 72, I'm placing here. Okay, like that 13 is less than 60, coming here, and less than 13, 25 is greater than 13, so I want to come to left. Again 13 is less than 15, I am coming to left side, I am placing here. Again 18 is coming here because less than, again it is less than, coming here, greater than this 15, so I am placing here. 47 coming here, and then greater than this 25, coming here, again greater than this 30, so I am placing here. Okay, 70 greater than 60, right side, again less than this 72, coming left. Again we are comparing with 68, so greater than this 68, I'm placing here. Like that 34. Okay, 34 is less than this 60, coming here, and greater than this 25, so I'm coming here. Again 34 greater than 30, coming here, but it is less than 34 is less than 47, I am placing left side. Okay, so now our task is over. They are asking what is the number of node in left subtree. So for this root, what are the, this is this side is left subtree. Okay, now how many nodes there? 1 2 3 4 5 6 7. Okay, so answer is A. Okay, so next one is consider the postfix expression with a single digit operand, the top two element of stack after second multiplication. So here if you are looking this postfix expression, here what happened, 6 2 3 star division 4 2 star plus 6 8 star minus. Okay, so now what happened? Okay, so you know the rule, right? whenever so if you are looking this postfix expression, you'll be having operator and operand, okay, and digits are all are single digit operand, and these are the operator. Okay, whenever from the postfix expression, if you are looking operand, we want to immediately push inside stack. Okay, so now 6 is in top. Now over that 2 we are pushing, then over that 3 we are pushing. Now star is coming. So what do you want to do? We want to pop out 2 top element from this stack. So now what will be top? So 3. You want to place right to this star. Okay, then next top element is 2. Okay, I want to place in left to this star. Okay, so now 2 into 3 is what? 6. Okay, and already 6 is there. Over that you want to place 6 again. Okay, now division coming. Now you want to pop out 2 more operand. Okay, what are the operand present in this stack is 6 over 6. Okay, now you want to pop out. I want to keep top 6 right to this division, and one more 6 is there. I want to keep in left to this division. So now 6 by 6 is what? 1. Again you want to reinsert in this particular stack. Okay, so now 1 is the present in the stack. Now 4 is coming inserting, 2 is coming inserting. So now what happened? Okay, so for in stack we have 3 element, 1 followed by 4 followed by 2. Okay, now second multiplication is coming. So for that I want to pop out 2 and keeping right hand side. 4 I want to keep to left to this multiplication. 4 into 2, 8. Okay, now again we want to push back into this stack. So now at the bottom we will be having 1 in stack. Over that we are pushing 8 of this result. Okay, so now 1,8 present in the top of the stack. Now you want to pop out and say what are two top element after this multiplication. Okay, now 8,1. Actually 1 over 8 will be there. So now you want to pop out, that will be 8 first we are popping, then followed by 1. So it is 8,1. Okay, so this is about stack postfix expression evaluation. With this I stop here. Thank you for watching. I will be continuing rest of the problem in next part. Thank you.